stoichiometry is a way that we can take complete balanced equations or even net ionic equations and do studies of the quantities of things that are made or produced or used up or whatever. So in a given reaction, by the way, the notes got better. I fixed it, which is great. We have that's not how that works. 4 molecules of ammonia react with 5 molecules of O2 and end up producing 4 molecules of nitrogen monoxide and 6 molecules of H2O. And while that's nice, it's not useful for us because what I could say from any of this is 4 molecules of NH3 needs 5 molecules of O2. Or I could say that for every 5 molecules of O2, I make 4 molecules of NO. Again, that's not really useful because we don't deal with molecules. What's nice though is that this all scales up to moles, and that's where the stoichiometry common core comes in. Basically, the common core says that the moles of A in a given reaction, where X is the coefficient for A, is a relationship to the moles of B, where Y is another stoichiometric coefficient. And so this is what we try to get to in quite a bit of the problems. Most of the time, we're just starting at one end or another, and we're trying to get to that common core. So, for example, let's try this out. How many grams of nitrogen monoxide can be made through the reaction of 10 grams of ammonia with excess oxygen? So this is my limiting reagent. It's the guy that's going to get used up first. So I'm in grams. In order to use a complete balanced equation, I need to get into moles. Many times this is going to be with molar mass. So if I have 10.0 grams of ammonia, I can end up doing my molar mass, 17.02152 grams in 1 mole NH3. And then using the mole-to-mole ratio from the common core above, I have 4 moles of NH3 to 4 moles NO. And then I want to know how many grams of nitrogen monoxide I make, so I need to go through the molar mass again. 1 mole NO to 30.0061 grams. Multiply across the top, divide by the bottom, and I have 17.6 grams nitrogen monoxide. Now that's pretty easy. Let's try something a little bit more difficult. So in this case, I have a white gold ring. There's the density of the ring with its volume. The alloy is 90% gold and 10% nickel. Now, gold won't react with hydrochloric acid, but nickel will. And essentially what it does is it forms nickel 2 chloride and hydrogen gas. So how many liters of hydrogen gas are formed at STP? So we don't even have to worry about what this means. We'll get there in chapter 6. Just know that it's a ratio. Anytime you see a ratio, it can be used in dimensional analysis. Just remember that. So I have this 1.0 centimeter cubed white gold ring. And you know what? I'm going to add in the WG on this just to show that. Now, for every 1 cubic centimeter of white gold, I have 15.7 grams of white gold. And then I know that the gold doesn't react, but the nickel does. So for every 100 grams of white gold, I have 10 grams of nickel. So now I'm in grams of nickel. If you couldn't see that, write these ratios out. 10 grams Ni per 100 grams white gold. But the problem is, after I get into moles, in order to get into HCl, I need a complete balanced equation. So a lot of times that's going to need to be the first thing you do. So in this case, it's nickel solid plus 2 HCl AQ goes to nickel 2 chloride AQ plus H2 as a gas. And this is what I want to know. So I'm relating two reactants. Totally allowable. I could relate two products to each other. I could relate products to reactants, reactants to products, or reactants to reactants. So the next thing I do is I go into moles. 58.69 grams in 1 mole nickel. Now I can go through common core. For every 1 mole nickel, excuse me, let me correct myself. We're going with hydrogen gas, so we're going to relate a reactant to a product, not two reactants. To 1 mole H2, and then for every 1 mole H2, I have 22.711 liters. Multiply across the top, divide by the bottom, and I end up getting 0.61 liters. Again, don't worry about what STP means yet. We'll talk about that once we get to gas law. But just look how we can relate these things. I accidentally said we could relate two reactants. That's not wrong. It's just that we don't want to do that here. If I wanted to know the volume of HCl used, then I would do that. If I wanted to know how much nickel 2 chloride I would make, I could do that. So let's do one more practice problem before we end this video. So I have acetic acid reacts with solid sodium carbonate to produce aqueous sodium acetate, water, and carbon dioxide. All right, so the first thing I need to do is balance out an equation. So I have acetic acid, H3O2 AQ, plus sodium carbonate, it's a solid, produces sodium acetate plus CO2 plus H2O. Balance it out, so I got 2 and 2. And that should balance me out. So if I have an aqueous solution of acetic acid, and I have the density, and I react it with 1.00 grams of sodium carbonate, what's the mass percent of acetic acid in the solution? So this is an interesting question, and it's important for us to recognize what's going on here. Mass percent is going to be grams AA, acetic acid, over grams of solution, times 100. So the first thing I'm going to need is my grams of solution. Then I'm going to need to determine my grams of acetic acid. And the grams of solution I can do with these two guys here. Grams of acetic acid I can tell by how much of it reacted. This is an important concept to realize, and this is where attention to detail becomes vital. You need to pay attention to what you're doing and how you're writing things. What are you looking at? What are you trying to figure out? So the first thing I'm going to do is come up with the grams of acetic acid solution. So I have 25.0 milliliters of solution, and this is where using at least an abbreviated form of the full units will help. And then for every 1 milliliter solution, I have 1.028 grams of solution. So I multiply across the top, divide by the bottom, and I end up getting 25.7 grams of solution. Now, dimensional analysis. I need to determine how many grams of acetic acid I have. So I start with my grams of sodium carbonate. Use my molar mass to get into moles. So for every 105.98874 grams, I have 1 mole sodium carbonate. For every 1 mole sodium carbonate, now I'm going to go into the common core. I need 2 moles of acetic acid. Now we're doing a reactant to reactant common core. And then for every 1 mole of acetic acid, you get 60.05256 grams of HC2H3O2. multiply across the top, divide by the bottom, I get 1.13, we'll take one extra 6 grams of acetic acid. To find the percent, I take 1.133 grams of acetic acid divided by 25.7 grams of solution multiplied by 100, and I end up getting 4.41%. A difficult problem. If you can't see that, try to work out a roadmap. You need to learn to write units with at least a little bit, right? If I wrote 25.0 milliliters, I might get confused and think that's 25 milliliters of acetic acid. It's not. It's the solution. So be careful with this kind of stuff.